And there's another one that we've been using. Okay, so I just want to make a distinction. You can, okay, so Newton meters is the same as joules, is the same as kilopascals. Okay, so any one of these three gas constants will work. I think the one that's in your data booklet is the 8.315 joule mole minus 1, K minus 1. But that one, you could easily just change it to the one with kPa. Okay, so they're equivalent. I do have a derivation somewhere. Do I have a derivation somewhere? Hold on. So I'm just trying to see. Okay, maybe after break I'll go back to this. But so just remember that you have like three versions of your gas constant. You can use either one. Okay, so we were talking about gases, and I think where we left off, we were talking about good grief, where were we with this? We're almost done. Yes, we were almost done. Okay. So we get into some stuff that they have in the textbook. It's kind of, so I'll teach it to you. But like I was saying about this note, I made it really heavy textbook based, and that's not, like if I was to teach this again, I wouldn't do it so heavily textbook based. Let me find my copy and then I'll fill it in. Where is my gases? What the heck? Is it possible that I find my note? Online people, if you're wondering what I'm doing, I'm madly scrambling to find my note on gases, which I cannot find right now. But you have to learn these equations. What am I going to do? Significant figure review, the mole concept, particle nature of matter, solubility. God, what did I do with it? Okay, you know what? This is weird. I can't find it. Okay, I'm gonna look for it one more time. Classic. We're on a wiki, you're wasting time, as usual. Mole ratios, mole concept, particulate nature of matter, review significant figures, empirical molecular formula. Should I double up on something? Okay, you know what we have to unfortunately do? Because I can't come up with these blanks from scratch. We're gonna move on to the next one, and then I'll fill this in when I find my note, which is probably on my desk in my office. Okay. So let's go to solutions. Hopefully these will be easier for you to visualize than gases. Okay. So solutions. Let me just give you a little bit of an introduction to these. Okay, whenever you see something like, let's say you have, for example, NaClAq. Okay. So that means that your NaCl is dissolved in water. So what you basically have is you have water, and this AQ means NaCl has become its ions in the water. Okay, so that's what we're talking about for the most part when we're talking about things being dissolved. Okay, when it's an ionic compound, it means that it's in the water and it's in its ions. So we're going to learn a bunch of definitions, but then we're going to learn how to work with solutions. Okay, so when we have a liquid, we can quantify it through, that should say volume, instead of mass. Okay, so basically if I asked you how much of a liquid you have, well, you wouldn't say that you have 2 grams of water, you'd say, oh, you have 2 milliliters of water, right? So that's how we sort of represent the amount of a liquid. We represent it with a volume. Okay, so liquids can be pure substances. Okay, where it's just water or bromine. So if you had just bromine, it would be a liquid. Just water, it would be a liquid. Just hexane, it would be a liquid. Liquids can also be solutions. Okay, so what I showed you up here with the NaCl, that's a solution. Something is dissolved in something else. Okay, so when I have a homogeneous mixture, when I have a homogeneous mixture of 2 or more substances, that is a solution. Okay, so it won't settle out. So if I dissolve some salt in water, it's not like that salt's going to fall to the bottom. It's going to stay dissolved. The water is going to kind of hold it up and spread it around. Okay, so a solution, it does not settle out. It's transparent. And cannot be separated by filtration. Okay, so I can't take a coffee filter, pour salt water through it, and expect the salt to stay on the filter. The solvent, that's the component that I have more of. The solute is dissolved in the solvent. So if I'm going back to my salt in water example, my NaCl is the solute. My water is the solvent. Okay, the one that you have more of is the solvent. The one that's dissolved is the solute. So your solution, we're used to seeing a solid in a liquid, but that doesn't always have to be the case for a solution. So if I have a solid dissolved in a solid, I can still call that a solution. So like a metal alloy, that's an example of a solid being dissolved in a solid. I can have a solid dissolved in a liquid. Okay, so like seawater, which is salt and water, or aqueous copper sulfate. So if I have aqueous copper sulfate, okay, I would have something filled with water. So Cu2 plus, SO4 2 minus, right? That's what copper sulfate dissolved in water would look like. Okay. If I have a liquid dissolved in a liquid, I have something like rubbing alcohol, which is alcohol, alcohol dissolved in water. I can also have a gas dissolved in a liquid. So if I have carbon dioxide dissolved in water, okay, that's an example of a gas being dissolved in a liquid. Okay, so we talked a little bit about solubility already, and we talked about will something be able to dissolve or not. So you do have these solubility guidelines. IB doesn't ask you too much about, with the solubility guidelines. But I do think it's good for you to be aware that something like that exists. So for solubility, okay, if I'm talking about solubility, that's a number, it's a measurement. So it's the maximum amount of a substance dissolved in a given volume of solvent. Okay, a lot of times it's how many grams will dissolve per 100 milliliters. Okay, and water. So you assume that water is your solvent unless otherwise stated. So your solubility, it's going to vary with temperature. Okay. So solubility increases with temperature for solids. So if I'm dissolving something, like if I'm dissolving even something like Kool-Aid in water, right? If I have warm water, I should be able to dissolve more Kool-Aid than if the water was cold. Solubility decreases with temperature for gases. So I don't know if any of you have fish. I can see some of you having fish. So basically, you don't want the water in your tank to get too warm. Why not? What do fish breathe? Fish breathe oxygen. If your water's too warm, what's going to come out of the water? Oxygen, yeah, because gases, the warmer your water is, the less the gas can be dissolved. Its solubility is lower. Okay, if I have a saturated solution, that's a solution where no more solute will dissolve at that temperature and excess solid is present, right? So if you have a saturated solution, you have the maximum substance dissolved. So if I'm trying to put more in there and stir it in there and put more in there and stir it, I'm going to get some of that substance on the bottom now because no more will dissolve. Okay, a supersaturated solution, that's when the solute concentration or its component ions exceeds its solubility. Okay, so it occurs if the temperature is changed or if a solute is produced in a chemical reaction. So the excess solid often forms a precipitate. Okay. Okay, we're ready to talk about concentration. Okay, so concentration. Okay, this is the amount of substance contained within a given volume of solution. You'll see when we write this value, you'll see what that definition means. Okay, so you have molarity. There's so many different units for concentration. Okay, so that's your most common concentration unit. It's moles of solute per volume of solution. Okay, and what is DM3? Liters, right? Liters. Okay. So C is equal to N over V. Okay, you could also use capital M equals N over V. So your units here are moles per liter. You could also write it mole per DM3. You could also write it mole per liter or M. So in the back, I'm not going to bring it out because I'm terrified of these compounds, but we have some really concentrated acids in the back. So what you'll see, it'll say sulfuric acid, and then it says 18M. So the 18M means 18 moles per liter, right? So if we had sulfuric acid in the back that had a 2M, 2 molar, that means you would have 2 moles of H2SO4 per liter. Okay. Okay, so if you see something in square brackets, that means the concentration of. So if I do this, NaCl in square brackets, what the shorthand is telling you is that the concentration of NaCl is 0.5 moles per liter. Okay, the concentration of sodium chloride is 0.5 moles per liter. Sometimes you'll see ppm. So that's parts per million. Okay, again, just thinking back to like the things I've seen for IB, I haven't seen parts per million a lot. If you were in 11 university chemistry, yes, you would have to do calculations with this. But just in case, like they ask you something about it, I put it in. Okay, so this is used for very low concentrations, like air or water pollution. Okay, so if you have 1 part per million, it means that each kilogram of solution contains 1 milligram of solute. Okay, so if you're calculating parts per million, you take the mass of your component, divide it by the total mass of solution, and times it by 10 to the 6. Okay, so if your density is 1 gram per centimeter cubed, 1 part per million means each liter contains 1 milligram of solute. Okay, so values of parts per million are based on mass, so they aren't temperature. Okay, if you see the word dilute, means that there's a small amount of dissolved solid. If you see the word concentrated, it means there's a large amount of dissolved solid. Okay, so a standard solution, that is a solution of known concentration. Okay, the mass of the solute is accurately measured and transferred to a volumetric flask. Okay, so when you see your lab equipment that looks like this is a volumetric flask, right? And it's very precise. So we use it to measure out something called a standard solution. Okay, it's accurately calibrated for a specific volume. So your solvent is added with swirling to help the solid dissolve until the solution level reaches the line on the flask. Okay. So we're going to do some examples. Okay, so let's take a look at the question and let's break the question down. Explain how you would prepare 100 cubic centimeters of a 0.100 mole per liter solution of sodium chloride. Okay, so you want to have you want to have 100 cubic centimeters, and you want your concentration to be 0.100 mole DM minus 3. Okay. So for a concentration, you need to weigh out. So what you need to do is you need to weigh out some amount of sodium chloride and put it into your solution. So let's see how much sodium chloride we'd have to weigh out. So I have 100 cubic centimeters. Do you remember how to go from cubic centimeters, like from cubic centimeters to DM3? Divide by 1,000. I can just take my decimal place and I can move it 1, 2, 3. Okay, so this is how much of the solution I want. Pardon? It's okay. Okay, so concentration equals number of moles over volume. So I want my concentration to be 0.100 mole DM minus 3. Okay. And I want my volume to be 0.100 DM3. Just moving this over to the side. Or just I'll do this with it. Okay, so let's isolate N. So times 0.100 DM3 times Okay, so this cancels. So 0.01 equals N. Okay, so I want this many moles of sodium chloride. Okay, so that's in moles. Now when I go to make my solution, I pour my 100 cubic centimeters of water, and then I go to put my salt into it, but this is moles. Can I weigh out moles on a scale? I can't weigh out moles on a scale, right? A scale takes grams, so what do I need to do? Right. So 0.01 mole times 1 mole, and the molar mass of sodium chloride is 58.44 grams. Equals 0.5844 grams NaCl. So significant figures, let's just say it's 3. Okay, so to make the solution, you would weigh out 0.5844 grams of NaCl and add to 100 cm3 water to a glass.
Miss, I have a question.
Yep, what's up?
Why do we need to put the minus for the DM -3?
Where?
Under the drawing of the container, it says 0.100.
Oh, okay. This is this is per liter. Yeah.
Oh, okay. Okay, thank you.
Okay, so this is like saying 0.100 mole per liter.
Oh, okay, I got it now. Thank you, Miss.
Okay, no problem. Okay, let's do another question. Okay. So the next question, calculate the concentration of a 0.04 mole per liter solution of sodium carbonate, Na2CO3, in grams per liter. Okay, so how do I do this question? Any strategies for this kind of question? Okay, I have 0.0400 mole per liter, and I want grams per liter. So what do I need to do?
Miss, do you find the molar mass?
Good, you find the molar mass. Okay, so let's find the molar mass of sodium carbonate, so Na2CO3. Okay, so it is, I added it up ahead of time, so 105.99. Okay. So again, that mole minus 1, that's just like having 105.99 grams per mole. Okay, so I have 0.0400 mole times gram mole, 105.99 grams per 1 mole. is equal to 4.24 grams. Okay, so let's use our shorthand for concentration. So therefore, the concentration equals 4.24 grams. Okay. 4.24 grams, so sorry, I should say per GM3. That one was easy. They get harder. Okay, so now we get to talk about something that I think is really, I really want you to be able to see and understand. For some reason, this is complicated for kids. I don't know if it would be complicated for you. I mean, hopefully not. But I wanted you to really be able to visualize the way something looks when it's dissolved and how a reaction looks when it's using dissolved components. Okay, so we're going to talk about net ionic equations. Okay, so this is, it's an alternative way of writing aqueous reactions. Okay, so you can write acid-base reactions this way, you can write precipitation reactions this way, you can write redox reactions this way. So let's say I have a chemical equation. Okay, so this is my standard chemical equation. And I have lead 2 nitrate plus sodium chloride gives me lead 2 chloride plus sodium nitrate. Okay. So I have two things that are dissolved in water. So the way that this would look, like if you were doing this reaction, you would have a clear solution. You would mix it with another clear solution. What does this solid mean?
Is it a precipitate that forms in the solution?
Beautiful, you get a precipitate. Okay, you get a precipitate. So the equation is nice because with the equation, you can predict what you're going to get. Okay, that's kind of the point of your standard chemical equation. However, it doesn't show you what's really going on here. Okay, so these equations have a place. It makes it easier to predict products and balance. But it doesn't show what's really happening. Okay, so let's take a look and see what's really happening here. And this is fancy now, I get to use my colors here. Okay, so PbNO3 aqueous. Okay, so PbNO3 aqueous. So I'm going to make this one green. Okay, so that means that lead 2 nitrate is dissolved in water. So in my solution, I have Pb 2 plus. Okay, NO3 minus, O3 minus. Why did I put 2 NO3 minuses? Look at PbNO3. Right, the subscript. I have 2 nitrates. Okay, I have 2 nitrates. So now I'm going to write 2 NaCl. Na plus, Cl minus, Na plus, Cl minus. Okay, why did I write 2 sodium and 2 chloride?
Because in the reactant,
Coefficient.
Right.
it's the ratio.
Beautiful. So for the NaCl, I have 2 of it, right? So now what I do is I pour these 2 solutions together. Okay, I pour them together, I mix them. So I mix, and here my PbNO3 gets mixed with my Na plus, Cl minus, Na plus, Cl minus. Okay, so my lead 2 nitrate gets mixed with my sodium chloride, and I've got all these ions together and they're all bumping around together. And when this lead meets the chloride, they're going to bump into each other and they are going to stick together and form a precipitate. Okay. Now, the sodium and the nitrate, notice how it's AQ? Well, they stay dissolved, right? They stay dissolved. So my 2 sodiums stay dissolved and my 2 nitrates stay dissolved. Okay, so the reaction, it happens between lead and chloride. My other ions are called spectator ions, right? They're not involved in the reactions. Like if you have a hockey game and you have spectators are watching, they're there, they're present, they're just not involved in the game. Okay. So this process that's going on in with my ions, right? This process, how can I write out a equation to show that? Okay, how can I write out an equation to show what's going on with my ions? To make it look a little bit more like what's actually happening in that solution. Oh, hydrated just means surrounded by water molecules. Okay, so surrounded by water molecules. Okay, that's hydrated. Okay, so let's take a look and see how we would write out what's going on with these ions. Okay, so over here, I have Pb2 plus aqueous plus 2 NO3 minus, and that's aqueous, plus 2 Na plus, that's aqueous, plus 2 Cl minus, that's aqueous. Okay, so this is before the arrow. And then there's my arrow. So there's my arrow. Maybe we can make it red. Okay, so now on the other side of my arrow, Pb reacts with Cl2 and it forms a solid, plus 2 Na plus Aq plus 2 NO3 minus Aq. Okay. So that's how I can show, excuse me, that's how I can show what's really going on in my reaction. Okay. Okay, so there's something called a net ionic equation. So your net ionic equation, it shows you what reacts. Okay, it doesn't bother with any of these spectator ions. So whatever is on both sides of the arrow, we can cross out. Okay, so what's on both sides of the arrow that we can cross out? So NO3 minus, right? I can cross that out. What else can I cross out? Right, sodium. Because those are my spectator ions, so they're not involved in the reaction. And then my reaction becomes Pb2 plus 2 Cl minus gives me PbCl2. Then that's it. Okay, so this equation that I wrote in blue, that is my net ionic equation. Okay, so it's basically saying any soluble lead compound that gives me Pb2 plus will react with any soluble chloride, which gives me Cl minus, to form a precipitate of lead chloride. I should say lead 2 chloride. Actually, no, don't put that 2 there. Your lead doesn't necessarily have to be 2. Okay, so that's when you get some of these reactions where it has aqueous. That's what's really going on in the reaction. It's not represented well by the chemical equations we're used to, but the chemical equations that we're used to, they're good because they help us predict products. Okay, so hopefully that makes sense to you. Okay, so dilution. And again, if you want me to go over anything, just ask. Okay, so a stock solution, that is a concentrated starting solution. Okay, so a lot of times, like our sulfuric acid in the back, our 18 molar sulfuric acid, that is a stock solution. I wouldn't work with 18 molar sulfuric acid. I dilute it before I work with it. Okay, so if a solution is too concentrated, solvent can be added to make a more dilute solution. Okay, so let's take a look and see what this would look like. So let's say I have 2 moles per liter. So here's a liter. I have a very big beaker, and here is a liter. So I would have 2 moles per liter. Okay, so there's my 2 moles. So now let's say I dilute it. Okay, so when I dilute something, I add more solvent. Okay, so I've added a liter of solvent, but I still only have 2 moles of solute. So now my concentration here is 2 moles per liter. Here my concentration is 1 mole per liter. So adding solvent, it decreases the concentration, but your amount of moles stays the same. Okay, so your amount of solute stays the same. Same number of moles. Okay, increasing the volume decreases the concentration. Okay, and we saw in our little diagram, we increase the volume, we decrease concentration. In both cases, the number of moles stays the same. Okay, so C1 equals N1 over V1. Okay, so for our first, let's say our first concentration here, okay, and C2 equals N2 over V2. So C2 equals N2 over V2. However, N1 equals N2. So we're just going to say that that's equal to N. Okay, so if we rearrange for N, C1 times V1 equals N. C2 times V2 equals N. So C1 V1 equals N equals C2 V2. And C1 V1 equals C2 V2. Okay, so you've got a dilution formula. So your volume units They don't need to be converted as long as they are the same on both sides. Okay, so you've got a nice little formula here. You've got formula C1V1 equals C2V2. Okay, we'll do a question using this formula. Okay, determine the final concentration of a 75 cubic centimeter solution of hydrochloric acid of concentration 0.40 mole per liter, which is diluted to a volume of 300 cubic centimeters. Okay, so I always like to draw pictures here. Okay. So I have 75 cubic centimeters. Okay, now this 75 cubic centimeters is 0.40 mole DM3. Okay, I dilute this to 300 cubic centimeters. Okay, so I want to know my new concentration. My concentration is going to be smaller because I diluted it. Okay. So initially, my first concentration is 0.40 mole DM minus 3. Okay, so I have mole per liter, right? So I am going to just convert that. So 75 cubic centimeters is 0.075 minus 3. Okay. So my second concentration, I don't know. I don't know what my concentration is when I dilute this to 300 cubic centimeters. But I do know that my second volume is 300 cubic centimeters. So 1, 2, 3. Okay. So let's plug that into the formula. So I have 0.40 mole DM minus 3 times 0.075 plus C2, 0.300 DM minus 3. Okay, so let's divide. And minus 3. This cancels. This cancels. Okay. So my final concentration is going to be 0.10 mole per liter. And that makes sense, right? I've diluted it. My concentration should go down. Okay, let's do another question. Our break's going to be soon. What time do we go? We go at 9:45. I know it's hard to sit for so long. It's hard for me to sit for so long. I've been wanting coffee since like 9 a.m. Okay. Calculate the volume to which 20 cubic centimeters of 7.63 mole per liter hydrochloric acid must be diluted to produce a solution with a concentration of exactly 5 moles per liter. Okay, again, I like to draw pictures so that I can visualize what's going on. All right, some people could just look at this and sort of crunch the numbers and figure out what to do, but I like to draw a picture. Whoops, that is a very slanty line. Okay. Okay, so I have 20 cubic centimeters of something that has a concentration of 7.63 mole per liter. Okay, so I am diluting this. So I'm going to dilute this. I don't know to what, but I want my new concentration to be 5.00 mole per liter. Okay. So we use our formula. So just a little, so 20.0 CM3, 1, 2, 3 equals 0.0200 DM3. Okay, so C1V1 equals C2V2. So let's say that this is C1, 7.63 mole minus 3, 0.0200 DM3 equals C2 is that. Let me just pull it over to the side. So 5.00 mole GM minus 3 times V2. Okay. 5.00 mole. This cancels. 5.00 mole. 3. My units cancel. So then when you crunch your numbers, you get 20. So let me just calculate this. I have something a little different in my notes, so. Seven point six three times 0.2 equals 0.03052. Yeah, DM3. We're looking for a volume. 4. 3.05. Whoa, no. 30.5. Okay, so to get a concentration of 5 moles per liter, you would need to dilute your solution to, oh my goodness, where's my mouse? To 30.5. Okay, so here you would need to add 10.5 cubic centimeters. So if you wanted to dilute your solution to 5 moles per liter, you would need to add 10.5 cubic centimeters. Cubic centimeters are milliliters. So you need to add 10.5 milliliters to get 30.5.
Miss,
Yep.
do we have to convert at the end to centimeters cubed?
No, you do not.
Okay, thank you.
You're welcome. Okay. So I'm not going to start the next question because it's going to take me more than 3 minutes to do, and it's coming up time for our break. So why don't we take our break, and then when we come back from our break, about 10 minutes, we're going to have 200 cubic centimeters, and we want our 200 cubic centimeter. We're going to pour some salt into it. Okay, so we want a solution, 200 cubic centimeters. Okay, so I want that much, and I want the concentration to be 1.5 mole per liter. Okay, so what I need to do is I need to weigh out some salt, put some salt into my beaker, whatever, and then make it up to 200 cubic centimeters. So I can't weigh out moles, so I have to weigh out mass. Okay, so let's figure out how many moles of salt we would need. So I want my concentration. So remember, C equals N over V, right? I want my concentration to be 1.5 mole per liter. Okay. And that means I have to put some amount of moles into 200, well, 200 cubic centimeters. Let's make that DM3s. So we just take that decimal point, move it 1, 2, 3. So 0.200 DM3. Okay. Okay, so now we're going to solve for how many moles we want of sodium chloride times 0.200 DM3, 0.200 DM3. These cancel. So DM3, DM minus 3. And I get 0.30 equals N. Okay, so that's how many moles of sodium chloride I need. So I don't have a scale that will tell me moles if I weigh it. So I need to take my amount in moles, and I need to figure out a mass. Okay, so that's grams per mole. So I have 58.44 grams per mole. And that is 17.532 grams. Okay. So significant figures, 18 grams. So the way that you would make this concentration, okay, so you would weigh out 18 grams of NaCl, place in a volumetric flask and make up to 200 cm. Okay, so typically in IB, you do a lot of something called a titration. So what I wanted to do was, you don't even know what that is, right? Like it's a technique in the lab. You don't know what it is. You don't know what it looks like. So I wanted to show you what a titration would look like, and then talk a little bit about it before we move on to some calculations with the titration. Okay. So honestly, if it takes more than one video, it'll take more than one video. So far, I've only found like one good video, but let's see. Okay, so online people, I have to do a little juggling here. Tab. Online people, can you see that and hear that?
Yes, miss.
Yes, miss.
Okay. It's really loud. Actually, it needs to be loud for my in-class people to hear it because I don't have speakers plugged in.
Good to see you.
Yeah, hey, what's with the polka dots?
What do you mean?
Polka dots are out. It's polka squares.
because the water pulls itself up the side walls of the glass. You should read the volume from the bottom of the meniscus at eye level. Secondly, it is important to read your volume to the correct number of significant figures. This burette indicates volume to the nearest 0.1 milliliters. With any graduated glassware, record the volume to one additional decimal place beyond the smallest graduation. In this case, record the volume to the nearest hundredth of a milliliter, estimating the final place. Use the volumetric pipette to transfer the analyte to the flask. Add a few drops of indicator to the flask and swirl. Place the flask under the tip of the burette. Record this volume. Placing a piece of white paper under the Erlenmeyer flask may make it easier to detect the color change. Operating the burette requires two hands. One hand turns the stopcock, while the other hand swirls the flask. Practice turning the stopcock a few times to familiarize yourself with how quickly the flow starts and stops. It is common laboratory practice that the first titration is an estimate. Open up the stopcock and allow the titrant to enter the flask quickly. Continuously swirl the flask. As the volume of titrant in the flask increases, the color of the indicator appears, then disappears as you swirl. When the analyte becomes a colored solution, close the stopcock. Record the final volume of the burette. Subtract the initial volume from this final volume to get the estimated volume of titrant needed for this titration. Knowing the volume that is a little past the endpoint, subtract 5 milliliters from that number to get the amount of titrant that can be safely added before a slower addition is required.
Okay, so you kind of saw it. I'm gonna go over it though, because where am I here? Let me set my entire screen. Okay, so what I want to do, and this is going to take me a little bit of time to do, but for your CPT, I do want to make it, it's not going to be like your IA, but I want to have a lot of elements from your IA in your CPT. So what I'm thinking of doing is doing a titration. It means I have to do the titration myself though and give you the data, and that's, I should get on that anyway. Okay, so let's take a look at this thing called the titration, right? You've heard the word, you kind of saw some of the equipment. So let's go over it. So the point of a titration is you have something where you don't know the concentration. Okay, so you would have an unknown concentration. Okay, so you have an unknown concentration of something. and you use something else where you know the concentration. So here you would have known concentration. Okay, so you would use something where you know the concentration to figure out your unknown concentration. Okay, so you have a solution where you know the volume and you know the concentration. Okay, so this is one. So here you've got one over here. You've got one in this tube called a burette. Okay, this tube is called a burette. And you have a second solution with a known volume, but you don't know the concentration of your second solution. Okay, so this is two. Okay, so you drip one into two. Okay, and a reaction happens. An indicator changes color when the reaction stops. At this point, the solutions are prevented from mixing anymore. Okay, so this solution here in your flask, it's going to change color. And when it changes color, you stop dripping because it means your reaction's finished. Okay, so then you figure out how much of solution one was needed for the reaction. And using this information, the concentration of solution two can be determined. Okie doke. Sorry, just stretching. Like honestly, I'm so much better in the evening. Okay. If this was like 7 p.m. at night, I'd be totally awake. Okay, let's move that to the top. Okay, so your stocks, so let's just read out what these like little labels say. So a different solution is poured into a calibrated burette that pours precise volumes into the conical flask. So this is a pipette. Okay, this thing here is called a pie pump. Okay, so you would measure out your unknown concentration using this pipette. Okay, so the pipette measures a known volume of one of the solutions into a conical flask. Okay, so this is your stock solution. Solution. Okay, that is your stock solution. So if you want to check the concentration of this one, you need to use something called the primary standard. It's available in very pure form. It has a relatively high molar mass. It is readily soluble in water. Okay. It is stable as a solid and a solution, and it reacts completely in a known matter. Okay, so let's take a really close step-by-step look at a titration. Okay, so what's going on a molecular level with a titration? This is titration is even something that you might do for your IA when the time comes. Okay. Now I don't know if this is big enough. Oops. All right, let's make it a bit bigger. Okay. Okay, so let's take a look at a titration. Okay, so let's say I have really big glassware, and I have a liter of HCl. Okay, so I have a liter of hydrochloric acid in my flask. Okay, so hydrochloric acid, and we were just talking about this, right? HClAQ. Well, how will that look? How will that look? HClAQ. It's dissolved, right? So what's your HCl going to become in the water? We were talking about this. It's going to be H plus Cl minus, H plus Cl minus. Okay, so I've got dissolved hydrochloric acid. Okay. And I know that I have 1 liter of it, but I don't know the concentration. Okay, I don't know if this is 2 moles per liter or 3 moles per liter or 4 moles per liter. I don't know that, but I do know that I have 1 liter of this hydrochloric acid. I'm going to find out the concentration of my hydrochloric acid by pouring in sodium hydroxide. Okay, so this doesn't really look like a proper titration setup. It was kind of the clip art that I could find. Okay, so I have Na plus OH minus. Okay, so that's what's being dripped in. Okay, so I'm starting my titration and I'm dripping in sodium hydroxide. Okay. So I drip in a liter of sodium hydroxide. So it's 1 mole per liter. Okay, 1 mole per liter. So I've dripped in 1 liter of sodium hydroxide. How many moles of sodium hydroxide have I dripped in? If I drip in a liter and it's 1 mole per liter, right, I've dripped in 1 mole of sodium hydroxide. So Na plus O. Why did I do this? Sorry, I need to make these a very precise size because I need to do something. Okay. Okay, so I drip in a liter of sodium hydroxide. So here, my hydroxide reacts with my acid, forming water. Okay, so I've neutralized a little bit of my acid, but I still have some H pluses, right? I still have some H pluses. So I drip in another liter of sodium hydroxide. Okay, so that's another liter of sodium hydroxide. So another mole of sodium hydroxide is dripped in. Whoops, I wrote that backwards. Na plus, OH minus. Okay. So when I drip in 2 liters of sodium hydroxide, I've completely neutralized my acid. Okay, no more H pluses, means I'm neutral. Okay, so after 2 liters of NaOH, the acid is neutral and an indicator changes color to show the reaction is complete. Okay, so at this point, something would change color to tell you that your acid has been totally neutralized. Okay. Okay, so what volume sodium hydroxide do you use? Well, I use 2 liters. Okay. So if I use 2 liters of sodium hydroxide, how many moles of sodium hydroxide did I use? 2 moles. Okay, so how much hydrochloric acid does that correspond to? So each OH minus corresponds to an H plus. So this OH minus corresponds to 1. So this OH minus corresponds to 1. So in total, I've neutralized 2 moles of HCl have been neutralized. Okay, so what is my concentration of hydrochloric acid? Well, I've had neutralized 2 moles, so there must have been 2 moles of acid per liter. Okay, so so when you're doing, so what I'm going to do, I'm just going to I'm going to put in some equations here. So let's say you didn't have the graphic, right? Let's say you didn't have the graphic and you had to sort of figure out this titration based on like formulas and equations. Okay, that's steps somewhere here. Okay, do I have some room? Yes, I do. Okay, so titration calculation steps.
Wait, Miss,
Yeah,
I have a question.
okay.
Why did we start off with 2 moles of hydrochloric acid in the?
It was just arbitrary. I could have started off with 3.
Oh, okay.
Okay. It's just like I just felt like making it 2 moles per liter. Okay. So titration calculation steps. So what you want to figure out first is how much. Okay, so you have a known concentration and you have an unknown concentration. So you have something where you know the concentration and something where you don't know the concentration. So the first thing you have to figure out is the volume of the thing that you know. Okay, then you figure out the moles of the thing that you know. Then you figure out your moles of the unknown. Okay, and here you would want to use a chemical equation. And then you would want to figure out the concentration of your unknown. Okay, so over here, we have, so our NaOH is my known. I know the concentration of this. Okay, so 2 liters, how many moles NaOH? Well, 2 liters times 1 mole per liter is 2. Okay, so that corresponds to 2 moles HCl. So here you need to use a formula. So HCl plus NaOH gives me NaCl plus H2O. Okay, so here I see that it's a 1:1 ratio. Okay, so then after I figure out my moles of HCl, I just put it over how many liters I had. Okay, we're gonna break down another one. And we're going to do something a little bit different for the second one. I just have to write a note to myself. Hold on. Okay, let's try another titration example. Oops, what did I do? Okay. Okay, so I have got, so I've got sulfuric acid, okay? I've got a liter of sulfuric acid. Okay, so here's my liter of sulfuric acid. So I've got H plus, SO4 2 minus, H plus, and again, I'm arbitrarily picking this, okay? Okay, so I've got, so that's what sulfuric acid would look like in solution, right? A bunch of H pluses and SO4 2 minuses floating around. And my H pluses are what makes this an acid. Okay, and I know my volume, I know I have 1 liter, but I don't know my concentration. I mean, you can kind of peek and figure out your concentration, but we're going to figure it out using a titration. So Na plus, OH minus. Okay, so first thing is I pour in 1 liter of sodium hydroxide. Now my concentration of sodium hydroxide is 2 moles per liter. So if I pour in 1 liter of sodium hydroxide, okay, how many moles of sodium hydroxide have I poured in? Okay, it's 2 moles per liter, and I've poured in 1 liter.
2 moles.
Good, 2 moles, excellent. So Na plus, OH minus, Na plus, OH minus. Okay, so I have neutralized some of this acid, right? So this OH minus neutralized some acid, this OH minus neutralized some acid. But I know I have to keep going with my titration because my solution's still acidic. Okay, once it's neutral, my indicator will change color. It's not neutral yet. So I'm going to pour in another liter of sodium hydroxide. So another liter of sodium hydroxide at 2 moles per liter. Okay, so I've neutralized probably the rest of my acid. So this H plus gets neutralized. This H plus gets neutralized. Okay, so at this point, my indicator changes color. Okay, so after 2 liters of NaOH, okay, the acid is neutralized. Okay, so there's no more H plus and an indicator changes, whoops, changes color. Okay, and that indicator changing color tells me my reaction stopped. So let's see if we can, do this mathematically. So what we sort of have here, let's see if we can represent it mathematically. Okay, so what volume of sodium hydroxide did I use? Well, I used 2 liters. How many moles of sodium hydroxide is that? So 2 liters times, my concentration is 2 mole per liter. So I have used 4 moles of sodium hydroxide. Okay, how much H2SO4 does this correspond to? So I need to connect my sodium hydroxide and my sulfuric acid in an equation. Okay, I need to make an equation here. So H2SO4 plus NaOH gives me Na2SO4 plus HOH. So I need to balance this. 2 hydrogens, I need to put 2 here. 2 hydrogens, 1 SO4, 1 SO4, 2 sodium, 2 sodium, 2 hydroxide, 2 hydroxide. Okay. So to figure out how many moles of H2SO4, okay, I'm going to take my moles of NaOH. Okay, so I use a mole ratio to determine that if I've used 4 moles of NaOH, that corresponds to 2 moles H2SO4. So that means my concentration of H2SO4 was 2 moles, and I started off, so I had 2 moles of H2SO4 in that liter that I started out with. So my concentration of H2SO4 is 2 mole per liter. Okay. Oh, I picked a hard one for you. I put the note that I put into this note is like, do an easier titration example before launching into this one. Okay, so let's read this over. It is found that 10 cubic centimeters of 0.2 mole per liter aqueous sodium carbonate requires 25 cubic centimeters of hydrochloric acid to just neutralize it. Determine the concentration of the hydrochloric acid. So let's draw what we've got going on here. Okay. So again, the values that I'm picking for here, they're just arbitrary. Okay, so I've got some sodium carbonate, right? So sodium carbonate, Na2CO3. So I've got sodium carbonate. Okay, and I mix it with acid. So hydrochloric acid, I mix it with some hydrochloric acid. Okay, so I'm not going to worry about the mechanism of my reaction, but the hydrochloric acid neutralizes the sodium carbonate. So for my sodium carbonate, I have 10 cubic centimeters. And then for my hydrochloric acid, okay, this is 25 cubic centimeters. So that's how much acid has neutralized my carbonate. Okay, So what we're going to do is we're going to set up some equations and they are going to help us find the answer. So what I might do, I might just go over this question quickly and then go over it in more detail tomorrow. Okay, so amount Na2CO3. So 1, 2, 3. So I have 0.01000 liters times 0.223 mole per liter equals, you know what? I hate that my calculator is just I'm not even going to say the word 1, 2, 3. 0.002 mole Na2CO3. Okay, so that's how many moles of Na2CO3 I have. So using an equation, I'm going to link hydrochloric acid and sodium carbonate. So HCl plus Na2CO3. And remember your carbonate neutralization. So I have NaCl plus H2O plus CO2. And is this balanced? So 2. Now I think it's balanced. 2H, 2H, 3 oxygen, 2 oxygen, 2 sodium, and 2 chlorine. Okay, so it's balanced. So I have 0.002 Na2CO3. Okay, let's see how many moles of acid that corresponds to. So I have 2 moles of acid for 1 mole of Na2CO3. So this cancels. So that means I have 0.004 moles of hydrochloric acid. Okay, so this is moles of hydrochloric acid. So now what I do, I just take my moles and put it over how many liters of hydrochloric acid I have. So 25.00 cubic centimeters of hydrochloric acid was used. So 1, 2, 3 equals 0.02500 DM3. So 0.004 mole over 0.02500 DM3 equals 0.0160 mole DM3. Okay, so that's the right number of sig figs. How many sig? I have 4 sig figs. Okay, so that is how many moles per liter of hydrochloric acid there was. Okay, let's save this. Okay, so we are going to be getting called down soon.